characterized surfaces and how to use them on radomes, for example. So let me first introduce you to the characterized surface feature. I have a few examples to share, and then I will go through a quick demo. Okay, characterized surfaces introduction. So characterized surfaces, they use pre-computed transmission reflection files. So it's when Feko, you have the option to calculate the reflection transmission coefficients, just like Gopi showed just now. And there you have the option to export them as a TR file. So basically there's then information for any angle, what is reflected and how, and what is transmitted and how. Yeah, and these files then can be used as characterized surfaces. So why would you do that? These can reduce the computational requirements. I mean, obviously, so if you have complex structures, spread it along large faces or geometry parts, then this means lots of triangles, and that means a lot of memory and runtime. With characterized surfaces, you do not have that problem anymore. So, and by that, this opens, for an important thing, this opens up the opportunity to optimize radome shapes, for example. Yeah, if you have complex FSS structures, for example, on a radome, and you change the shape of it, this is not only a lot of work, manual work, but to edit the shape, but it's also, again, then a lot of runtime and memory. So how to get these TR files? You can either use the periodic boundary condition approach, just like Gopi showed, or another option would be the multi-layer Green's function method, where you basically only have multi-layer dielectrics without any additional geometry in it. These are the two ways. So in any case, you need an infinite surface in X and Y. So that is either planar Green's functions or periodic boundary conditions. You may have theta and phi variation. One nice thing is that you can also, if you calculate the TR file, then obviously normally you would need all the angles. Like you go theta from 0 to 180 and phi from 0 to 360. But if you have a structure which behaves the same in all directions, I mean, for phi, for example, then it's sufficient, obviously, to have only one theta cut. And this will then also work. You can also have frequency variations, so you can have both in one model. So quite some freedom here. Okay, here's the workflow. So this is the important slide. You start here. This is what Gopi basically showed. You have either a PVC structure or an infinite multilayer dielectric structure. You calculate the TR file or the reflection transmission coefficients. Here you see various plane wave angles have been defined, in this case with an increment of 8 degrees, for example. So this results in a whole lot of angles. You need to tell the solver that both calculations, both orthogonal polarizations should be calculated. And then you calculate transmission reflection coefficients and export them to the TR file. And this then contains all the information we need. Okay, solver is running, TR file is being created. Now in another model, you may add this TR file for a characterized surface definition, like you see here. You just right click on media and say, give me a characterized surface, and then Feko will ask you for the TR file. And there you go. And then you calculate the whole thing with RLGO. So this characterized surface feature basically is meant to be used with RLGO. We also support MLFMM. This is often forgotten. Even I tend to forget it here and there. But yeah, I will come back to that later. RLGO is what it's actually meant for. Here is what you see, how it looks, or how it can look in post-Feko. What are these angles here? These show the orientation of the characterized surface. So you see here in Cat Feko, when you define a characterized surface, or not when you define it, but when you apply it to a face, then you have to tell the solver the direction. Yeah, yeah, I will come back to that again in the live demo. Some tips here. Yeah, as always, of course, don't forget to perform a mesh conversion study. I know that rarely ever anybody does that, but yeah, to be sure, increase or decrease the mesh size, run again and see if results are stable. Theta 5 frequency resolution study, investigate using single theta, blah, blah, blah. Okay. For validation, of course, if you have really large structures, you will not always be able to compare with the reference full wave model without the characterized surfaces. So then it may make sense to have a reduced model and then compare. Yeah. Okay, yeah, we can skip that. A few examples. I guess it's 2 examples. So you see here a 31 times 31 plate made of these crosses here, and it's calculated both with MLFMM and with one single phase using characterized surfaces in RLGO. And here you see the comparison between the near field, electric, and magnetic. Seems to work quite okay. Another example here, without any comparison in this case, it's an FSS radome at 10 gigahertz, and TR file is used, RLGO is used, and the runtime is, you cannot even get a coffee in that time, right? You see the results, but yeah, here what's missing is the comparison with some reference model. I will show that with my own model, which is given here. So this is what I'm gonna demo in a moment, but I take already now here the results or the computational requirements. So this is the radome model. I built it myself. It's not a real radome, of course. I made it myself. It's basically a sphere, a part of a sphere. It has 3 dielectric layers, and between the top layer and the middle layer, there is this FSS structure, which is identical to the one that Gopi just showed. Yeah, here you see the PBC model. This is then the MLFM model, which was, yeah, I was able to construct this in Cat Feko actually by using the project operation with a flat FSS structure and then projecting it on these curved faces here. And I guess the distortion is quite minimal, so I was able to accept that. And here you see the RLGO model. And here's the results compared. Quite okay, I would say. And looking at the memory and runtime, MLFMM, 81 gigabyte of memory and half an hour runtime compared with 11.5 seconds of runtime for RLGO. And yeah, looking at these here, these numbers, I guess that these differences at some angles are acceptable. Okay, demo. So I was thinking what exactly to demo, since Gopi now already showed the periodic boundary condition feature. Let me open Cat Feko here. And show you the finalized model. Yep, let me quickly see where it is. It's this one. So yeah, like I said, this is almost identical to Gopi's model. The only difference really is that I have these 3 dielectric layers added here, just to give the FSS some support, else all the elements would fall down, and you know how expensive copper is nowadays. And in any way, this of course shifts the resonance of the minimum transmission coefficient. It shifts from 8 gigahertz, I guess, down to 5 or 6 or something. Let me open the results of this model. just very quickly, we neglect any warnings as always. So this is my transmission coefficient here. Yeah, it shifts from 8 down to 6 gigahertz, but for me, I didn't care. What I want is a radome that is more or less transparent at 10 gigahertz, because this is where my horn antenna is gonna radiate, which I'm gonna show you now. Just a second. So this is a radome, or this is actually the middle phase of the MLFMM radome, which you will see in post-pico in a few seconds. And what I did is, here's the geometry, here's the phase. And what I did is I added a characterized surface to it. Characterized surface was created here using the TR file that came from the PPC model. That's it. That's really all the magic. Important thing here, maybe the U vector of the characterized surfaces by default, it's something like this. So this would in this case mean that the cross is rotated by 45 degree, and this is then a difference to the MLFMM model. So in my case, it would be either like this or like this. It doesn't matter because, yeah, you know the shape. Okay, let me get you to the results quickly because time is running. So this is the MLFMM model, which serves as our reference here. You see quite complex, but still not a big deal for MLFMM. You see there's this FSS structure on the top of the middle layer. Let me quickly show it to you by hiding the dielectric here. So this is how it looks. You see how the crosses is located like this. And now let me add the RLGO model as well. And let's have a look at the results here. So this is MLFMM. Let's have a look at the E field in decibel. And this is then the RLGO result. Yeah, this is quite good comparison, I guess. All right, let's get back to the slides. Just a quick summary. Characterized surfaces offer the possibility to replace complex FSS structures. Obviously, that's the benefit here. Yeah, you can use either planar Green's functions or periodic boundaries to calculate the TR file. One of the main benefits from characterized surfaces is basically having the opportunity to optimize radome shapes, which would not be possible with the actual physical modeling of the elements on the structure. Yeah, before I forget, MLFMM is also supported. So when you want to use MLFMM with characterized surfaces, just one thing to keep in mind: you need one dielectric region. So the CS structure must be the boundary between the dielectric region and the free space. So typically what I do is I add a thin air region, and that should then also always work. And maybe I have an example here. Not even sure if I have it still. It's, I guess, this one. Yeah, characterized surfaces with MLFMM. I have it. Nice. Now taking this result as well. Yeah, again, quite good agreement. Quite good agreement. Now I have to tell you one thing. I used the spherical mode source here. You see here, and it's a bit close to the structure. Yeah, but I just accepted it. So there are warnings about this, and still the results to me look reasonable. So I just ignored it. So if there are deviances, it may be due to this. That's all from my side. Questions, welcome in the chat.